Okay, let me get started then. Well, welcome everybody and good morning. And I'm delighted to be able to be here in a virtual world for today's talk. So today I'd like to focus more on science than applications and talk about how modern deep contextual word representations effectively learn linguistic structure. The backdrop for our discussion is the task of language modeling. So in language modeling, you've got a sequence of words, or at any rate, a context like the students open there, and then you're trying to predict what word in this case comes next. So it might be they open their books, or they open their laptops, or they open their exams, their minds, and all of these words are likely words, but then there are lots of other words that aren't likely words. So it's unlikely that the word is microphone. It's unlikely that the word is hand, wrist, etc. So a language model in general is this method of predicting words in context. And language models have been a key part of all of the success of probabilistic and then neural NLP over the last about 4 decades now. And they're widely used in tasks like speech recognition, spelling correction, and any natural language generation task, including machine translation, summarization, and story generation. So back in the dark ages before modern neural networks, the standard way of building language models is you simply counted how often word sequences occurred, and by doing a simple division of counts, you got a probability estimate. So if you wanted to work out how likely different words are after President Trump denied thee, what you could do is say, well, we couldn't do this with too big a context because of the curse of dimensionality. So let's make a Markov assumption and perhaps only use 2 words of prior context, denied the, and then we could simply count in a large amount of text how often denied the accusation and denied the occurred, and do a simple division that would give us a probability estimate for accusation being the next word. It couldn't be quite that simple because there are a vast number of words, and so there's then a lot of sparseness in the counts that we could calculate. And so much of the energy and work of these language models was working out how to discount and smooth the models, or use mixture and back-off models to address that sparseness. But even at this time, these models were very successful for any kind of applied applications like machine translation or speech recognition. And you might have thought, how did these relate to models of the structure of language as linguists knew about them? And at that time, the general attitude of linguists was, even if these models were useful from an engineering perspective, that they just were linguistically completely uninteresting, because although they know a certain amount of word knowledge, and in some sense they know some low-level syntax, they know you get sequences like preposition, article, or noun, they have nothing of what linguists like to describe in the structure of languages. There is no concept of noun, there are no sentence structure rules, there's no form of abstracted grammar. And so because of that, in natural language processing as well, the general understanding was, well, if we wanted to be able to do sentence understanding, we needed to be able to understand the structure of sentences. And the only way that we were going to be able to approach that task was to have human beings by hand annotate a lot of data, annotate text for part of speech, for grammatical structure or syntax with tree banks, and for things like coreference of pronouns and other forms of coreference. That this was the only path forward to build these resources and then do supervised learning. And in some very general sense, that corresponded to the dominant position in theoretical linguistics. So most famously, Noam Chomsky has argued for 50 plus years, that the evidence available to little children is too little for them to be able to learn the structure of human languages. And therefore, it must be the case that the children are getting a lot of help by means of having innate linguistic structure. And the mechanism was different with the construction of resources like tree banks, but in some sense, the claim was the same, that this material couldn't just be learned from the observed data alone. So there's been a lot of progress since then. So we moved into the era of neural language models. And the first step of that was Yoshua Bengio's famous work in the early 2000s, where essentially, rather than having these very sparse categorical models, he showed how you could instead use low dimensionality distributed word vectors, and then you didn't have any of the sparseness, and the models could share statistical strength between semantically related words. That was then augmented by moving to recurrent neural network models, which allowed the modeling of long contexts. So you have sentences like this one from an Arthur Miller short story, the same stump which had impaled the car of many a guest in the past 30 years and which he refused to have removed. If you want to predict the word that is going to occur after he refused to have, looking at the last 4 words isn't very much help. But looking in the past 30 years and which doesn't help much more either. To know that removed is a good candidate word to place next, you really have to look all the way back to the word stump or perhaps impaled. And that's the kind of thing that n-gram language models could never do, but you could hope that a recurrent neural network model could do. On the other hand, in an example like this, you could also think of the syntax of human languages, because there's another way in which these two words are closely connected, that the stump is actually the subject of removed in this sentence. So maybe if we knew grammatical structure, we could also do this prediction task much better. So when I got back into looking at neural models of language about 2010, that was actually the leading idea I was principally wanting to capture. How could we build neural networks which had explicit tree structure that could capture the hierarchy or recursion in human languages, and so that we could be modeling not just a word sequence, but the structure of sentences. And so we built models like tree LSTMs, which we use somewhat successfully for tasks like sentiment analysis. So in an example like this one, the model could correctly tell that the words a waste were negative and good performances was positive. And then when these words were combined into the bigger phrase, a waste of good performances, that was overall a negative description. So the central idea that we wanted to be capturing was precisely that in human languages, a sentence's meaning is composed via the syntax tree. So if you have a sentence like the chef that ran to the store was out of food, and you're wondering who or what was out of food, that it's wrong to think it's the store because the store occurs close by to was out of food. Rather, it's what the tree structure here shows, that it's the chef that's the subject of was out of food, and the words that ran to the store is then a relative clause that's modifying chef. However, as anyone who knows the slightest bit about NLP knows, this isn't the direction in which work in the field has headed. So in particular, if we focus in on just the last 3 years, we've seen these enormous breakthroughs in natural language processing coming from using very large language models as a universal pre-training base, as a way to give deep contextual representations of a word token in context. So rather than a vector for a word type, as in older models like Word2Vec, we're now having a representation for one particular instance for word in context. And this started off with models like Elmo and OMFET, and then it rapidly expanded with lots of other models, the GPT series of models, the most famous one of all, which I'm going to talk about mainly now, the BERT model, and then a whole bunch of others, XLNet, Ernie, Albert, etc. And central to these is the adoption of transformer models. So except for the first instances, all of these models are transformer models, which are very efficiently trainable at large scale on GPUs. I haven't got time to go through all the mechanics of a transformer model in my talk today, but to give just an inkling of how they work. So at the bottom, we have word or actually word piece representations and positional encodings. And so we have, for training a BERT model, we've got some context, judiciary committee report, and then we're wanting to predict a masked out word in that context. And the way we do that is starting off with the word representations. We project from those via linear transforms, that is a matrix multiply, a query vector, a key vector, and a value vector in a lower dimensional subspace. And then we use the query vector at one position to calculate how much attention to pay to every word in this piece of text. So we're calculating with a dot product an attention score by taking QV dot products, which we normalize in the softmax to have an attention distribution over the words of the text. And then we use that attention distribution to weight the values at each position, and we create a weighted average of these values and then start to use those. But rather than doing that only once, we think, well, maybe there are lots of words in the context that could be useful in different ways. So we calculate multiple queries, keys, and values off of each word, say 12 of them, and calculate 12 of these values, which we combine together in a new hidden representation for this particular word committee and context. But we don't stop there. We have a very deep model. So we repeat this whole operation, say 12 times, to have a deep contextual language model. There are a lot of other details, but the simple important things to remember is that these models are all based on doing attention calculations, and that they're centrally using these softmax operations, which have a sparsifying effect because most of the weight goes to the most important words. These models have had tremendously positive effects in all areas of NLP. I'll just give one very quick example here. So the Allen AI Institute has worked for about 15 years on its flagship project, Aristo, of trying to build systems that could answer scientists' questions. When the project was started, this was seen as a way to rejuvenate work and knowledge representation and reasoning. But in the last couple of years, they've had enormous new success in this task. And the way that they've had that success is not doing any of that, but instead using very large BERT-style models. And so you can see here that they could get very good performance with Aristo BERT, which is simply BERT model trained on a lot of science text. And then by going to some of the more recent BERT-style models, such as Aristo Roberta, they could do even better. Both of these models perform way better than the...
You know, this morning, yesterday, you must use these things to log out, right?
Huh? I'm getting interference now. Both of these models work way better than the knowledge-based systems that they'd developed previously. And while they have ensemble model, which does a teeny bit better than the individual models, you can see nearly all of its performance is coming from the performance of Aristo Roberta. Well, in these BERT models, it's interesting to actually think about what are they actually doing. And so what we can do is we can start to poke at these models and understand what they're doing. Well, we talked before how there are these many attention heads. So something we can do is look at the attention heads at each word position and see where the BERT model is paying attention. And so the simplest thing to do is look for each word and each attention head at each layer and see what is the most attended to word or words for each head. And what we're interested in is, are these models starting to learn anything about human language structure? Well, if we do that at low levels of the model, we see simple behaviors. So there are some heads that attend broadly, roughly a bag of words style head. But that sort of makes sense, because once you're beginning to want to understand how to predict, an obvious thing to do is to look everywhere and see what's out there. And some heads look at the previous word or the next word basically uniformly. And again, that's simple, but it makes sense, because everything we know from 40 years of empirical NLP is that if you're only going to look at one thing, looking at the previous and next words is the single most useful source of information. But once we get higher up into the BERT models, we can see some more interesting behavior. And so in particular, we can start not wanting to know whether BERT models capture the syntactic structure of sentences. And an obvious way to do that is to look for them learning evidence of dependency syntax structure. So in a dependency parse tree, each word is a dependent of some other word. And so that we can have that I is the dependent of went as the subject of the sentence, and the main verb of the whole sentence, went, we take as a dependent of an extra root token like this. So we could take these dependencies and compare them to a tension that we find in our BERT-like model, and can see if some of the heads are capturing syntactic structure via dependencies. And indeed, we find that they are. So the 10th head at the 8th level, it seems to be basically picking up having direct objects attending to verbs. Actually, not just the head word of the direct object, but all words in the direct object. So here we have Paine-Weber considered an even harder sell, and all of an even harder sell are attending to considered. Recommending specific stocks, both specific and stocks are paying attention back to recommending. The 11th head at the same level seems to have noun pre-modifiers, articles, numbers, adjectives attending to their head noun. So the complicated language and the huge new law. So the complicated, both those words are attending to language. In the huge new law, the huge new is all attending to law. And indeed, a prepositional modifier, the preposition will also actually attend to law, as you can see there. So that's pretty cool. We have these specialized heads that really know about the syntactic structure of sentences. It turns out that we don't only have heads that know about syntax, we also have heads that know about phenomena like coreference. So coreference is different word mentions that refer to the same entity in the world. So when we have with Kim today, as she got some expert opinions on the damage to her home, Kim, she, and her all refer to the same person. And what we find is that she, for head 4 at level 5, is attending to Kim, she, and her is attending to she and her mainly, and sort of slightly up to Kim. It's not only with pronouns referring back to a name like Kim. So in this example here, joining peace talks between Israel and the Palestinians, the negotiations are ... The talks and the negotiations are also co-referent, and head 4 is also having these pairs of words attending to each other. So what we seem to have here is two very simple but key neural tools, attention and softmax, that are being able to model the symbolic structure of human language sentences really well in a somewhat soft way, but well, it's well known that language has a kind of softness rather than a rigid grammar like a programming language. So soft structure is probably better. We can look at that in one other interesting way. So rather than looking at individual attention heads, we can look at the representations that are being calculated at higher layers. And we could ask the question is, do these deep contextual word representations just actually capture the syntactic structure of a whole sentence? And initially you might wonder, how could we tell that? Because there are these big floating point vectors. How can we relate those to a tree? But a good way to relate them to a tree is to use distance metrics. So we can put a distance metric over a tree. So going back to this sentence that we saw before, the chef who ran to the store was out of food, precisely with chef being the subject of was, that the word chef is close to was in the tree. It's at distance 1, which is just counting these tree arcs, where the store is far away because it's distance 4 away from was. So we can have a metric of distance on trees, and then we can represent that to distance inside our vector spaces. So here's how we can do that. So we have contextual word representations, and these are high dimensional space. Obviously, I'm just sort of showing 2 dimensions in my picture. Well, we can't just use these as is because, well, a lot of these word representations are going to be representing other things, you know, among other things. Meaning is much more of a sentence than its grammatical structure. But we could suppose that some small part of the representation captures the syntactic structure of sentences. And so the way we're going to find it is we're going to do a linear transformation. So again, multiplying by a matrix, which will take us to a relatively low dimensional space. You can do this with about 32 or 64 dimensions. And so we're going to map these contextual word representations to this low dimensional syntax space. And the learning we will do of a syntactic probe is simply to find a good low rank B vector that best maps the contextual word representations into a syntactic space. And then in that space, our hypothesis is that squared L2 distance in that space will be a good representation of tree distance. And so under that assumption, we can simply say, let's find the minimum spanning tree in the syntax subspace, and that will be the syntactic structure of the sentence. And if you do that, it turns out that it actually works pretty nicely. So if you have baselines, so you could put a linear chain structure on every tree because English trees are sort of basically right branching to a fair extent, or you could use the same model architecture, but then just have a randomly initialized model above it. None of these things work very well. But if you look at the contextual representations learnt by BERT, learnt first by Elmo, the simpler model, or even more so with BERT, a nearer to state-of-the-art model, we find that these models actually have very good syntactic representations. So they were actually doing reasonably well as a parser at being able to reconstruct the tree structure of these sentences. We'd also like to have a representation of just depth in the sentence, and we can also model that by calculating the norms of words. And if we do that, we find that these models actually do a very good job at representing depth in the tree as well. So here's just one example of that overall. So the black above is a human annotated dependency parse tree, and the teal below shows our minimum spanning tree. And as you can see, it almost exactly gets correct the human assigned parse structure of the sentence. There's just a little bit of an error here, reflecting actually a very common problem in grammar induction systems. It's very hard not to get these common preposition article sequences grouping together. And so this is really interesting. So effectively, in these modern deep contextual language models, we see a phase change in their behavior because they're such flexible parameter-rich neural networks. Rather than simply learning word associations of words to the left and the right, we find that the model has enough capacity and can find enough value in knowing about syntactic structure that some parts of the model specialize and learn hierarchical linguistic structure because it's useful even for this simple word and context prediction task. We can go a little bit beyond that and say, what happens if you try and do this not just for one language, but across multiple languages? Modern linguistics has suggested a universal grammar that underlies all human languages. Is it the case that a BERT representation can have this kind of common language knowledge that allows effective transfer from one human language to another? We can test this by using multilingual versions of deep contextual representations, such as MBERT, Multilingual BERT. So we can train a syntactic probe on representations in one language, such as English, and then we can evaluate it on another language, such as French. If that works, this intuitively suggests that the way MBERT encodes English syntax is very similar to the way it encodes French syntax. And what we find is that that does indeed work. So the baseline is, again, a randomly initialized BERT model, which doesn't do very well at capturing syntax. For understanding the structure of one language, we can train directly on the evaluation language, which is like what I showed before for English. But if instead we train on some other language and then project across, we can already get sort of most of the way from the baseline to training directly on the test language. If we train on 9 other languages, we can get even closer to it, that we can get sort of 70 to 80% of the way there. I'll just show a couple of pictures that point in the same direction. So we're training on English, and then we're looking at the representation of French dependencies. And in particular, we're going to look at whether this model learns about grammatical relations like subjects and objects and adjectival modifiers. And note in particular, even though the probe gets told a little bit about tree distance, it never sees and gets shown no information whatsoever about grammatical relations like subjects and objects. But what we find is that the model learns representations where not only are there clusters for grammatical relations like determiners, adjective modifiers, subjects and objects, but these actually cluster between French and English. So the sort of more washed out colors are English and the more saturated colors are French. And what we see in basically all cases is that we have the same relation in English and French actually grouping together in this shared syntactic subspace. That doesn't happen for our random baseline, where you mainly just get a mess. And to the extent that you get something other than a mess, you get individually very common words of one language forming a cluster. Here's one more picture of the same sort. So my final thoughts are, it's been amazing how successful unsupervised or self-supervised learning has been in this language model context. You might think that just predicting a word in context is a sort of a simple, shallow task, but it actually proves to be a very rich universal task, because all kinds of information, such as syntactic structure, knowing about coreference, knowing about topics and domains, discourse structure, are all useful to do this task better. And in fact, we're having such success with these kind of models. It's now seeming that the work of the last 30 years of hand annotating lots of linguistics data may turn out to have, in the long run, have been a mistake, that we can actually learn about linguistic structure by just building these large self-supervised models. And the key thing that I think is interesting is precisely that these deep contextual word representation models, once they become rich and large enough, they seem to phase shift from being simple statistical association learners to actually models that discover the structure of human languages. And I've in particular focused on how language syntax emerges in the geometry of BERT models. And that's actually a very surprising finding from the sort of understanding of human language and linguistics. There's one just final thought I want to end on is all of these gains are great, but they've been done within this distributional approach to meaning, which is where we're just trying to predict words in the context of other words. That's not how most people have thought about semantics, regardless of whether you're thinking of programming language semantics or human language semantics. By far the dominant approach is denotational semantics, which links word and sentence meaning to states in some world model. So you're linking the word chair to objects that are chairs. We've gotten a very long way with distributional approaches to meaning, but it could be that now we really do need to be refocusing work and starting to focus more on grounded models of language learning for the next decade ahead. Thank you.
So thanks, Chris, for this wonderful talk. Actually, I'm really impressed by how this statistical driven model actually can discover structures. And no, I mean, for NLP, one of the holy grail is to understand the language structure. And it seems like for simply predict the words, give you all the information you want. That's amazing. Yeah. So actually, I received quite a few questions from the audience, and I will ask them. I think we still have like a 1 or 2 minutes for a question. So one question is like this. Although we have a lot of representation methods, as far as I know, they are still based on statistics. So Chris, do you think that the machine can really understand human language? Because sometimes when I generate summary from the article, there still exist grammatical errors, fact errors, etc. Chris?
Right. So sure, yeah. So I gave a very positive story, but you know, things clearly, it's not that we've solved the whole problem of human language understanding, and that there are lots of places, whether it's summarization, question answering, or machine translation, where we also see the shallowness of these models and their failures of understanding. You know, I'm sure that simply by continuing to develop these models of the last 3 years, we will continue to push some of the numbers up. But that's essentially relates to my last bullet point of refocusing on grounded language learning. I think ultimately we're never going to get models that have a good understanding of the world until they start to be models that have some understanding of the world, rather than models that are simply, you know, doing what's sort of playing a game of sort of trying to predict words in the context of other words.
Great, thanks, Chris. Yeah, actually, I like your idea about how we learn language from grounded or other facts, things like that. So I think there's still many questions, but I think we don't have enough time, and we can leave this question as a panel stage, and the people can ask more at that stage.